Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. Vector bundles can be studied via transition functions because you can always trivialize a vector bundle, and the transition functions are what allows you to reconstruct that vector bundle by gluing the trivializations together. Furthermore, two different transition functions will give you isomorphic vector bundles if they differ by a change of trivialization. And so if you look at transition functions modulo these change of trivializations, you will get what are known as cohomology classes, and that allows you to classify vector bundles as cohomology classes. What I want to show you in this video is how you can do something fairly similar in the Galois theoretic setting. So remember, if you want to look at transition functions, essentially that gives you what's known as descent data in the usual topology. But you can look at descent data in other Grothendieck topologies as well. So we want to look at the Grothendieck topology that you get from Galois theory. And that will give us Galois descent data. And the corresponding cohomology theory will be Galois cohomology. So let's look at the setup that we want to give here. So the setup is the following. Firstly, we fix a field F. And we look at Galois covers of this. So K over F is a finite Galois extension, say with Galois group G. And we look at twisted forms of this. So basically, twisted form of some object I'll write as M underline of K. So this is something that you should be able to define over F, and also you should be able to pull back over such things as these finite Galois extensions. And the example to keep in mind is MNK. So this is the K algebra of n by n matrices in this. So a twisted form of MNF that's split over K just means that some F algebra, such that when you tensor it over F up to K, you get a K algebra, and that K algebra is isomorphic to M and K. And we've seen that these are precisely the central simple algebras over F. So what we need now, of course, is how we do the gluing, and that corresponds to automorphisms. Okay, so we'll need the automorphisms of this object. I'll denote generally this is A underline of K. That's the automorphisms in this case of Mn of K. And in this case, we can write down what this is quite nicely, because we have the Skolem-Noether theorem, which tells you that every automorphism of this MnK, this algebra, K algebra of n by n matrices in K, comes from conjugation. So it comes from some invertible matrix inside GLNK, and if you conjugate by that, this will give you an automorphism, and the only way that two invertible matrices will give you the same automorphism is if you differ by a scalar matrix. Okay, so the ones which are trivially on here, of course, are just the scalar matrices. So this is just the quotient of GLNK by the scalars. One thing to note here is this A underline K, just like this M and K, the Galois group will act on this and will also act on this A underline K. It acts on this M and K, of course, just by, well, you just act on each of the entries inside here. And hence you also act on this automorphism by conjugation, and it will correspond to, well, if you pick an invertible matrix inside here and you look at the class up to scalar, you just act on each of the entries inside there. Okay, so the next thing that we need is that, remember, this K over F you should think of as being the analog of an open cover which trivializes, okay, in this case, algebra. Okay, so what you want to look at next is, when you look at the open sets in a cover, in the vector bundle case, you look at the intersections of two of them at a time. That's how you want to glue. And then you want a compatibility condition which involves the triple intersection. So the intersections of two at a time correspond to K tensor over Fk. Remember, this is the dual of the fiber product. Okay, and one thing that we've seen is that this is isomorphic to the product of G copies of K. So there's one for each element tau inside the group G. And the isomorphism, I'll change it from the usual one because I want to use a different indexing. Y tensor Z will map to, okay, it's going to be a tuple, one for each tau inside G, and that will send this Y tensor Z in the tau coordinate will be tau of YZ. Similarly, the triple tensor product is isomorphic to a product of K with itself, now G cross G times. So we need two elements, sigma and tau, inside G. And what's the value there? Okay, so the value there is x tensor y tensor z will be sigma of x tau of y z. And this follows fairly easily from the way I've written it there, and that's part of the reason I chose this presentation here. Okay, so what we can do is we can apply the first isomorphism to the second two. So this y tensor z will go to tau y z for each of these taus. And then we apply again, because this is now a product of k's, you'll get k tensor a product of k, so we apply this again. So we now have another element of the group, sigma. Sigma applies to the first one, sigma of x, and then we just multiply by the other term, which was tau of y z, and that's how we get this second isomorphism here. Okay, so now we want to look at descent data, and in the case of the general theory, okay, you look at the projections onto the first and second factor, and we have fiber products. We've dualized things here, so here we want to look at k maps to k tensor fk in two ways. We can slot the x either into the first coordinate, so I'll make this one the first, this is on the second, so this is x goes to 1 tensor x, or projection 2, which is x goes to x tensor 1. So really these aren't projections, okay, but I've used the type of notation as if it were in the geometric setting. So this is due to perhaps what you'll expect. So what type of data was descent data? So the descent data here should be a map from projection 2 upper star of this m underline k to projection 1 upper star of m underline k. Okay, so remember you've trivialized, so you get m underline k, and then what we're going to do is we want to do the pasting, and this is how you work out the pasting or the gluing data. So let's work out in this particular Galois theoretic setting, what are these objects here? So here you have m underline k, and you want to tensor this by k tensor f over k. And then this, there's a, the x goes to this thing here, okay, 1 tensor x here. So basically, this second x will get absorbed into the k inside this k algebra here, so that's m and k. And there's an extra k floating around here. So this is k tensor f, m and k. That's the nicest way to think about it, so that you can see kind of what it is, and how it also differs from projection 1 upper star of m underline k. So now, because this projection 1 upper star, you've got 1 tensor x, okay, the x is flopping around here, so you get this instead. Okay, so now let's go to this, see what happens. Now, when you do this tensor product, you can slip the k inside here to get m and k tensor fk, and now apply this isomorphism here. This is just a product of k g times, so you can pull that product out. So this is the product of g copies of m and k. So the main thing, don't worry too much about what's happening here. It's not so important, okay? For the fine details, the most important thing is that you can rewrite this as just g copies of m and k. And you have an isomorphism of g copies of m and k like this to this g copies of m and k, and it should be as over this object here. So as algebras over this product of g copies of k. So what's the upshot of this? So we need an isomorphism of this as algebras over here. So that means that you need an isomorphism on each component. Okay, so theta is really given by, for each component, so for each sigma inside G, okay, I'm going to give you an isomorphism from MNK to MNK, which is essentially just an automorphism of MNK, or an element of A underline of K. So sigma gets mapped to this automorphism. I'll denote it F subscript sigma. And we can think of this as a function, or you can also think of this F as a tuple F subscript sigma, one coordinate for each element sigma inside the group. So remember now, what we want to do here is we want to show you that work out the analog of transition functions, and transition functions can't be arbitrary. So remember, if you have three patches where you trivialize, okay, you can try to glue the top patch to the bottom patch, the bottom patch to the top patch. Okay, you can do that directly, or you can go from the bottom patch to the middle patch, and the middle patch to the top patch. And if you compose those two, it should be the same as going directly from the bottom patch to the top patch. Okay. So basically, the co-cycle condition is going to be projection 1, 3 upper star of theta is equal to projection 1, 2 upper star of theta composed with projection 2, 3 upper star of theta. And what I want to do is I want to rewrite this condition where this theta now is written in terms of this f. So let's go and see how that works. So firstly, the original formulation in terms of theta, you work with k tensor fk. And what are all these projection upper stars? Okay, so this projection 1 to upper star will send x tensor y to this triple tensor product 1 tensor x tensor y in the 1, 2 slot. Projection 1, 3 means that you insert a 1 in the second slot. And projection 2, 3 means you insert a 1 in the first slot here. Okay, so we want to change this language. So basically to get this, right, I just use these isomorphisms here. So let's use those isomorphisms on the two sides. Okay, so when I use the isomorphism here, what do I get? So here I just get according to this formula here, except for I'm indexing over sigma in G. So there's a sigma, the first one, times just the second one. So sigma of x, y. Okay, and that's going to be my function f sigma. If I apply it on this side, we have to use the second isomorphism, in fact b. Okay, so 1 tensor x tensor y. If you have 1 tensor x tensor y, the x is 1, so you just get this bit here, which is tau of x, y. Tau of x, y, that's the value at sigma tau. Okay, so remember there's going to be one of these elements of k for each sigma and tau inside the group. X tensor 1 tensor y, so y is 1, so you get sigma of x, y, sigma of x, y. And finally, when z is equal to 1, you get sigma of x tau of y, sigma of x tau of y. Okay, so that's what you want to do here, right? Now really, this f sigma, perhaps it's not really an f sigma. Okay, this f sigma now will consist of now elements inside a underline of k. So not in k, these are elements inside k, right? What happens when you're inside k? But they're inside a underline of k. So you should think of them now as, for example, up to scalar, just an invertible matrix whose entries are in k. So the entries will look like this. Or alternatively, I guess a better way to think about it is you can think of this x and y as invertible matrices, okay? And then they're invertible matrices with entries in k, and then sigma will act on each of those entries inside that invertible matrix, okay? So you can let sigma act that way, okay? So now f sigma, the type of object, it'll look a bit like what you get here, but x and y will be like invertible matrices, okay? So you can think of it that way, or you can think of this as just automorphisms that you get, where each of the entries kind of looks like that, okay? So how do you go from here to here? Okay, so what's the analog of projection 1, 3 star, projection 1, 2 star, projection 2, 3 star? Okay, so I'll call them D3, D2, T1, corresponding to these three here. So how do you go from F sigma, okay, which will have entries like this, to this one here? Well, basically, if you look at what's going on here, this is just the entry that you have here when sigma equals tau. When sigma equals tau, you get tau of xy, which is this one here. So that means if you take an f sigma, f, okay, and you want to do this D3, which is the top one here, projection 1, 2 upper star, okay, to get you something with entries like that, you just look at f tau, okay. What about D2? To go from here to here, you just look at f sigma. So it's D2f, the value at sigma tau, okay, only depends on the sigma, and it's going to be f sigma. And finally, what's the last one? If you want this f sigma like this, so it's given by entries like this, and you want to take it to entries like this, okay, I claim the correct thing to do is at sigma tau, it's going to be tau dot f subscript tau inverse sigma. Okay, so this is a little bit harder to see how this works out, but let's just have a look at this. So firstly, what is this f subscript tau inverse sigma? So the entries will look like tau inverse of sigma x, y. Tau inverse sigma, if you apply tau to it, will get you sigma of x, that's the correct thing. And since tau is multiplicative, you'll get a tau of y here. So that's sigma of x tau of y, which is exactly what you have here. So that tells you that D1f, if you look at the sigma tau, coordinate of that is tau, you let that act on f tau inverse sigma. Okay, so tau here is acting on this element inside here. So you should think of this as just, remember, invertible matrices up to scalar, so you can let the Galois group act on each of the entries inside that matrix. Okay, great. So this actually allows us to rewrite our co-cycle condition. Okay, so projection 1, 3 star, that's the middle one, D2, will be just F sigma. Projection 1, 2 upper star, so that's the top one here, D3, is just F tau. And you compose that with projection 2, 3 upper star of theta, that's this one here, tau dot F tau inverse sigma. And this has to be true at each coordinate, so for each sigma and tau. Okay, so that's what you have. Usually we don't write the co-cycle condition in this way. We change variables slightly. We replace, since this is true for all sigma and tau, we can say it's for all, we can let sigma equal tau sigma, okay? And then they'll range through the same thing. So if tau sigma is tau sigma, you get F subscript tau sigma. And then here, the sigma occurs also here, so you get just sigma. So F tau sigma equals F tau composed with tau dot of F sigma. Okay, and this is true for all sigma and tau inside G. So if you've seen Galois cohomology, this is the usual way we write, or one of the standard ways to write the co-cycle condition, the one co-cycle condition. Okay, and there are some things to note about this. So firstly, remember we said that the descent data is given by a function of this form from G to A underline of K. And the first point to note is that, well, maybe you think it's the correct condition that this is a group homomorphism. Okay, so if this were a group homomorphism, that means that F underline tau sigma equals F tau composed with F sigma. And here we see that we don't necessarily have that condition, unless of course tau is acting always trivially, okay? But in this case, we can see tau does not act trivially, okay? So the group doesn't act trivially because the group acts on each of the entries inside here, okay? So it's not a trivial action. So this is not the usual action. So what's going on here, and what's the easiest way to think about what's going on? Well, the best way to describe it and to connect it with what we've been looking at before is to have a think about how, in the previous video in this playlist, I constructed Hamilton's quaternions using this sort of a theory. Okay, so we saw that Hamilton's quaternions is a twisted form, okay, of 2 by 2 matrices over the reals, and it's split when you extend scalars to the complex numbers. So it's actually a subalgebra, a real subalgebra of 2 by 2 matrices over the complex numbers, and there is a corresponding action of the Galois group of the complex numbers over the reals. So that's just a cyclic group of order 2, which involves conjugation. So you can actually just look at the invariance of that, and you should be able to recover Hamilton's quaternions. But the way you let that Galois group act is not the trivial way, okay? It's not the standard way. You don't just take conjugation in each of the 4 entries inside 2 by 2 matrices over the complexes, okay? If you look at the fixed string there, you'll just get, well, each of those entries has to be fixed by conjugation, so it's real, so you just get 2 by 2 real matrices, okay? So that's the trivial case. So what we did instead is that we twisted this Galois action, okay? And the way we twisted this Galois action is that instead of looking at that action, we first apply that action where we conjugate each of the entries, and then we compose it by conjugation by some fixed matrix that I came up with. And that's an automorphism of that algebra. So we do the same thing here. We don't have the usual action. Remember, this group G acts on M and K because this here is just the so the group acts on M and K because it acts on K. Okay, so that's kind of the functorial nature this is, that you have here, and hence it acts on this automorphism group. And the easiest way to see this also, or another way to see this, is that you can think of this as just invertible matrices up to scalar, so you can act on each of the entries inside that invertible matrix. Okay, so so what we're going to do is we're going to change the action of tau to not just tau, but we're going to compose that with this automorphism of M underline K. That's given by this one cocycle F tau. Similar sigma goes to F sigma sigma. And if you want to get a group action so that G acts, that means that tau sigma gets mapped to the thing when you compose these two. And when you compose these two, the tau doesn't commute through the F sigma necessarily. To push it past, you'll have to let tau act on the F sigma, and then you'll get F tau composed with tau dot F sigma, tau sigma. So essentially what you want is this condition here means that if you define a new action of this Galois group on this m bar k, not the trivial one where you just act on each of the entries, but you twist it using this one cocycle, then you will get a group action precisely when this one cocycle condition holds. Okay, so let's finish up by giving some definitions which connect how this theory is just like what we see for studying vector bundles via cohomology using transition functions. Okay, so the first thing is what is the analog of the transition function? Okay, so the data is just a function f from the group to the automorphisms of that object over k. So A underline k, because in this case it's this object here, PGLNK. And this function is called a one cocycle if this condition here holds. Okay. So the set of these is the set of one cocycles Z1G A underline. And so the next question is, well, suppose you're given two cocycles F and G. Okay. When do they produce isomorphic twisted forms? Okay, so in the case of vector bundles, okay, when do you get isomorphic vector bundles if you have two different transition functions? Well, essentially what happens is that you can change the trivialization. That's all you can do. So remember, we're assuming you have a twisted form that's split over k. So that's your trivialization. And so if you change trivialization, you change by an automorphism. So it's an element of A bar k. That's what you can change. So we say F and G are cohomologous if essentially it's given by some x inside A underline k, the relationship between the two. And what is that relationship? It's the following. Okay, so basically G sigma, the G, its value at sigma is gotten from F sigma via using this x. You basically conjugate by x, but in a twisted way. So instead of doing x F sigma x inverse, you change this x inverse to sigma dot x inverse. Remember, sigma acts on this group here, so you can let that become sigma dot x inverse. So since this is a group and you're looking at a group acting on it, okay, this gives you an equivalence relation, and the equivalence relations are called cohomology classes. And this set of cohomology classes H1G A underline actually classifies all the twisted forms of m bar, well really f, okay? So twisted forms of that which are split over k. So when you tensor up by k, you get this, okay? So that shows you how you can use now cohomological methods to try to study twisted forms and things like central simple algebras, just like when you try to study vector bundles using cohomology theory. I hope you enjoyed this adventure in pure mathematics.